Resolution. Resolution is the foundation of everything. It's the total number of pixels your GPU draws on screen per frame. 1920 by 1080 is 1080p. 2560 by 1440 is 1440p. 3840 by 2160 is 4K. Each step up roughly doubles the pixel count. And double the pixels means double the work. Think of your GPU as a painter. Resolution is how many brush strokes it makes per frame. More strokes means more time. More time means fewer frames per second. Physics, not settings. The jump from 1080p to 1440p is 1.78 times more pixels. From 1080p to 4K is exactly 4 times. So if you're averaging 120 frames per second at 1080p, native 4K could realistically drop you under 30. That's why render scale matters. It's the hidden version of this setting, buried in most games but hugely impactful. Render scale at 100% means the GPU renders at your actual screen resolution. Drop it to 75% and the game renders fewer pixels, then stretches the image to fill the monitor. It looks softer, but it can buy back 20 to 30 frames per second instantly. Always check render scale before you touch anything else. Half the time when a game runs badly, render scale is already sitting at some weird number you never set. Texture quality and anisotropic filtering. Textures are the images wrapped around every 3D surface in your game. The cracked concrete wall, the wooden floor, the stitching on a character's jacket. Without textures, your entire game world would look like a preschool art project made out of colored clay. Texture quality controls how detailed those images are. Higher settings use larger, more detailed texture files. Lower settings save memory, but make surfaces look flat and smeared, like the artist gave up halfway through. Here's the important part. Textures don't destroy your frame rate. They eat VRAM. If you have 8 GB of VRAM, high textures at 1080p and 1440p are fine. Try to force ultra textures at 4K on a 6 GB card, and you'll see stuttering, pop-in, and textures loading one chunk at a time. That's VRAM overflow. Your GPU starts pulling from system RAM, and everything slows down. Set textures as high as your VRAM handles without stuttering, then forget about it. Anisotropic filtering pairs directly with textures. It sharpens surfaces viewed at steep angles. Roads stretching into the distance, floors across a large room. Without it, those surfaces blur into a smeared haze. With it at 16 times, distant surfaces stay sharp and detailed. And here's the best part. Anisotropic filtering has almost zero impact on modern hardware. Set it to 16 times, never touch it again. Anti-aliasing diagonal edges in games produce a staircase pattern. Tiny jagged steps along rooftops, railings, character silhouettes. That's aliasing. Anti-aliasing is the setting that smooths it out. And there are several types, each with different trade-offs. FXAA is the lightest option. It blurs the entire final image very slightly to soften jagged edges. Fast, cheap, works on any hardware. The downside is that everything gets slightly soft. Fine details like thin wires or text can lose crispness. MSAA is more precise. Instead of blurring the whole image, it targets only the geometry edges. Much cleaner output than FXAA, significantly heavier on the GPU, especially at 1440p and above. TAA, temporal anti-aliasing, is the modern default. It uses data from previous frames to reconstruct smoother edges over time. It handles static scenes beautifully. The trade-off is ghosting. Fast-moving objects can leave faint trails. Some players never notice. Others can't stop noticing. That's gaming. DLAA is NVIDIA's AI-based version. It runs at native resolution and uses machine learning on tensor cores to clean edges. Sharpest output available if your card supports it. Also the most demanding of the anti-aliasing options. For most builds, TAA is perfectly fine. On RTX hardware and a stable frame rate, DLAA is worth enabling. If performance is tight, FXAA is a reasonable fallback. MSAA is for people who value image precision over frame rate. Shadows are the single most GPU-intensive visual setting in most games. They're also one of the most impactful on how the scene looks. Remove shadows entirely, and a game immediately looks staged. Objects float. The lighting feels wrong. The whole world looks like a theater set where someone forgot to add depth. Shadow quality controls the resolution of shadow maps. Think of shadow maps as the images the engine uses to calculate where shadows fall. Low quality produces blocky, pixelated shadows with hard, unnatural edges. High quality gives you soft, accurate shadows that behave like real light. Shadow distance controls how far into the scene shadows are rendered. On low settings, distant trees and buildings cast no shadow. They look like cardboard cutouts standing in sunlight with nothing beneath them. High shadow distance extends that realism deep into the environment. Contact shadows are the smallest and most overlooked. These are the tiny shadows directly where objects touch surfaces, under a chair leg, leg, where a rock sits on a floor, between your character's feet and the ground. Without them, characters look like they're hovering just above every surface. Once you notice it, it's impossible to ignore the honest reality. Shadows will cost you more FPS than almost any other single setting. If you need performance headroom, this is where to make your compromise. Medium shadow quality with context shadows on usually strikes the right balance. Ambient Occlusion. Ambient Occlusion adds subtle shadow to spots where light naturally struggles to reach. Corners where two walls meet. The gap under furniture, between stacked boxes or rocks. Without it, lighting feels distributed evenly in a way that looks artificial. Objects sit in a space but don't feel like they belong to it. Turn it on and everything settles. Depth appears. Surfaces feel grounded. SSAO is the most widely supported version. It approximates occlusion using on-screen pixel data. Fast, compatible with most hardware, noticeably better than nothing. HBAO Plus is NVIDIA's version, and it's a meaningful step up. Sharper output, full resolution, runs more efficiently than the original HBAO. In any game that offers it, HBAO Plus is the right choice. Ray-traced ambient occlusion runs the full calculation using actual ray tracing, physically accurate to a level SSAO can't match. Performance cost is real, typically 10 to 15% on its own. Here's a simple test. Disable ambient occlusion in a game you know well. The scene will immediately feel slightly wrong, objects slightly flat, light slightly fake. That's your brain noticing the missing depth information. It reads as subtle in screenshots, but it's constantly working in the background. Ray tracing traditional lighting in games is approximate, pre-baked into textures, simulated with math shortcuts. Clever, convincing, but never physically real. Ray tracing changes the equation. Instead of approximating how light behaves, it simulates it. Rays of light bounce from sources, reflect off surfaces, pass through glass, scatter through fog. The result is lighting that follows physics instead of mimicking it. Different games apply ray tracing to different elements. Some apply it only to reflections. A character's visor reflects the actual game world instead of a blurry static image. Some apply it to shadows, giving them soft natural edges that shift with light sources accurately. Others use it for global illumination, meaning indirect bounce light fills rooms the way real sunlight through a window does. Path tracing is the complete version. Every light bounce, every surface, every interaction, simulated simultaneously. Games with full path tracing can produce stills that look photographed. The GPU cost is substantial. Upscaling becomes essentially mandatory to maintain playable frame rates. If you have the hardware, selective ray tracing on reflections and shadows is visibly worthwhile. Full path tracing is the next generation your wallet will remind you of immediately. Upscaling. This is the most important performance technology in modern gaming, and most people still treat it like a compromise instead of a tool. Upscaling renders the game internally at a lower resolution, and reconstructs a sharp image at native resolution using software. The goal is near native image quality, at a fraction of the actual GPU cost. DLSS from NVIDIA uses AI trained on enormous amounts of reference data to reconstruct detail. Quality mode renders at roughly 67% of native resolution. At viewing distance, the difference between DLSS quality output and true native is genuinely difficult to spot. Performance mode renders at 50% and can effectively double your frame rate. FSR from AMD is hardware agnostic. It works on NVIDIA, AMD, and Intel cards equally. It uses a spatial algorithm rather than AI training. FSR4 closed the quality gap significantly. For non-NVIDIA users, this is the go-to. XeSS from Intel also uses AI and runs across all hardware. On Intel Arc GPS, it operates at full AI quality. On other cards, it falls back to a non-AI path that competes closely with FSR. Frame generation is the next layer. After rendering a frame, the GPU predicts and inserts an additional frame between the existing one and the next. This can near double displayed frame rates. The trade-off is slight input latency because those frames are predicted, not rendered from your inputs. For single-player games, largely fine. For competitive shooters, something to weigh carefully. The bottom line, if you're not using upscaling in 2026, you're leaving performance unclaimed. DLSS quality and FSR quality at 1440 ABET and 4K produce excellent results. Use them. Quick question, are you running upscaling or holding out for native resolution? Drop it in the comments. And if these settings are starting to make actual sense, hit that like button. It genuinely helps the channel. VSync, GSync, and FreeSync screen tearing happens when your GPU outputs a new frame while the monitor is mid-refresh. The result is a visible horizontal slice through the image. Half the old frame, half the new one, cut across the screen. VSync fixes this by holding frames until the monitor is ready. The problem is that holding frames introduces input lag. Your mouse clicks and controller inputs feel delayed. That disconnect between action and response is real and measurable in gameplay. GSync and FreeSync solve this more elegantly. Instead of holding the GPU back, they tell the monitor to adjust its own refresh rate to match GPU output in real time. Your GPU outputs 74 frames per second, the monitor runs at 74 Hz. Tier free, no held frames, minimal added lag. GSync uses NVIDIA's proprietary hardware built into certified monitors. FreeSync is AMD's open standard and supported on a large number of panels. NVIDIA also certifies many FreeSync monitors as GSync compatible, meaning you can run adaptive sync on them with an NVIDIA card. card. Check your monitor model. You might already have this working without knowing it. If any form of adaptive sync is available to you, use it over classic VSync. The difference in how inputs respond is significant enough that going back to VSync feels permanently wrong. HDR expands the range between your display's darkest blacks and brightest highlights. The keyword is display. HDR is a hardware feature first, software feature second. For HDR to actually deliver what it promises, your monitor needs to hit meaningful peak brightness. 600 nits is the entry point for a noticeable effect. 1000 nits and above is where HDR genuinely pops. Explosions that look bright in a dark room, shadows with actual depth instead of muddy gray. A monitor marketed as HDR capable at 250 or 300 nits cannot deliver real HDR. The game sends the signal, the hardware can't produce the range. Often it looks worse than SDR because the game's color grading assumes display capability that doesn't exist. If you have a qualifying display, enable HDR in both windows in the game, then calibrate both. The result in games that implement HDR well is a noticeably different image with more perceived dimension. If you don't have the hardware for it, skip the setting entirely. It will not improve your experience on an SDR panel. Motion blur and depth of field. Motion blur adds simulated camera blur to fast movement. In film, this is natural. Cameras have a physical shutter. Games render complete frozen frames. Motion blur adds back the cinematic in-motion feel. The gaming community is split directly down the middle on this. Competitive players turn it off immediately. Camera motion blur during fast turns blurs information and slows reaction processing. Cinematic single-player players often leave it on. It softens the mechanical look of rendered frames, a practical middle ground. Per object motion blur on, camera motion blur off. Moving objects like vehicles and projectiles look natural. Turning the camera doesn't smear the entire screen. Depth of field blurs objects at varying distances from the focal point. Nearby surfaces stay sharp. Everything else softens. It mimics real optics and adds perceived depth to scenes. Some players leave it on. Others find it limiting when they want to see the full environment clearly. Both settings carry modest GPU cost. In performance-limited situations, disabling both is a clean trade with minimal visual loss. Post-processing is the filter layer on top of everything else. It doesn't change geometry, lighting, or textures. It adjusts the final completed image for stylistic effect. Bloom makes bright light sources glow and bleed into surrounding pixels. Sunlight cutting through leaves, neon signs in wet streets. At moderate levels, it adds atmosphere. Too high, and every light source looks like it's having an episode. Chromatic aberration mimics lens distortion by splitting edge colors into visible red and blue fringing. It adds a film camera quality. Many players disable it because it competes with the sharpness they aimed for in other settings. Film grain overlays visual noise to evoke analog film stock. In dark atmospheric titles, it can add grit and character. In most games, it's purely preference. Performance cost is negligible for both. Vignette darkens the corners of the frame slightly to pull focus toward the center. Usually kept subtle in modern games and usually doesn't need attention. For most setups, chromatic aberration and film grain are off. Bloom at moderate levels stays on. But this is one area where personal preference is genuinely the right answer. LOD and render distance level of detail, or LOD, is how games manage geometry budget across distance. Objects close to the camera render at full polygon count and full texture resolution. Objects further away get progressively simpler versions, fewer polygons, lower resolution textures. The transitions happen quietly in the background. By the time detail drops, you're already too far away to notice. Render distance controls how far into the world any objects draw at all. Low render distance makes trees materialize out of thin air. Mountains assemble as you walk toward them. High render distance extends the visible world correctly. Environments feel continuous and real. In open world games, render distance is the most expensive setting per FPS point. Every additional meter of visible world is more geometry to process, but it's also one of the most noticeable settings visually. Standing at a high point and seeing a full environment stretched to the horizon makes a game feel genuinely massive. If you're making cuts, textures, and anti-aliasing first, render distance last. Final suggestion: here's exactly how to approach a new graphics menu. Start with resolution and render scale. Lock your baseline frame rate, then shadows. Tune them down until you hit your target FPS without frame drops. Then upscaling. Enable DLSS quality or FSR quality. Watch your headroom return. Set anisotropic filtering to 16 times. Done. Textures at the highest your VRAM handles without overflow. Ray tracing only if you have genuine headroom remaining after everything above. The goal is never maximum settings. The goal is the best image quality your specific hardware can sustain at your target frame rate. Smart balance beats brute force every time. Now here's the thing. You just learned what every graphics setting does and exactly what each one costs. But there's a number plastered on every single GPU listing that determines how many of these settings you can actually use. VRAM, 4 GB, 8 GB, 12 GB, 16 GB, 24 GB. Most buyers stare at those numbers without knowing what they mean for the games they actually play. Buy too little and textures stutter. Ray tracing crawls and no amount of setting adjustment fixes your experience. Buy too much and you just pay for performance you'll never touch.